So from here on, so none of this that we covered had anything to do with neural networks, right? But it was important to understand the context, and I'll tell you why it was important to go over the traditional way of learning word representations, and then we'll see how it ties to the modern way or the neural network way of learning representations, right? So we'll start with the first neural network based model for learning word representation, which is known as the continuous bag of words model, okay? So just to set the context, the methods that we have seen so far are known as count-based models, right? Because they rely on these co-occurrence counts for learning representations of words. And the methods that we are going to see now are called prediction-based models, and it will become clear shortly why the term prediction and how they learn the word representations, right? So in a way, in the original thing, there was no learning involved. Of course, you can say that you are trying to learn these eigenvectors and eigenvalues and so on, but it was not in the same way as we have been learning parameters of a neural network and so on, right? It was not in the same spirit. But now, once I do these second type of models, this distinction would become very clear. One, why is there a learning involved, and why they are prediction-based models, okay? So the story ahead is we are going to look at continuous bag of words model, then something known as skipgram. So this is the famous word-to-vec model which you guys have already started looking at. Then we look at glove word embeddings, which is some kind of a hybrid between the count-based models and the prediction-based models. And then we'll see how to evaluate word embeddings, and then end with this depressing note that good old SVD is just fine, right? So all the progress that has happened in the past 5-6 years, you could just use SVD and still go by, but if you do that, you'll probably not get a job, right? So you have to learn these things, okay? So now let's start with the continuous bag of words model. So consider this task, and just bear me for a few slides that why this is connected to our problem and all that. So I'm going to consider a task where you have to predict the nth word given the previous n-1 words, right? And this is something that you do regularly, sometimes even in the class when you are WhatsApping or SMSing. So this is what you do, right? You start typing he sat on a, and you get this prompt that the next word should be chair or something like that, right? Now you can think of this as a classification problem. Can you tell me why you can think of this as a classification problem? Can you tell me what is, so remember that we have always thought of this, that there's always a y, there's always an x, and then we're trying to learn this relation from x to y. So given this example, can you tell me what is x here and what is y here? Everyone is clear about that, right? So this is x and this is y. Now I made a statement that I could think of this as a classification problem, right? So the minute I say classification, what is the y that comes to your mind? A dash hot y, one hot y, okay. Anything else would have been inappropriate, but okay. So one hot y is what you would expect there, right? And now what's the size of this one hot vector? Size of the vocabulary. So you are trying to predict one of the words in the vocabulary. Okay, so you see why this is a multi-class classification problem? You see that? There are many classes and you want to select one of these classes. Now the moment I say classification, I give you an x and y, now you'll start asking me who will give me the training data for this. So can you think of training data for this? Any corpus, similar to the one that you are creating, right? In specific, what you will do is, suppose you have framed it as the following problem, that you are given 4 words and you want to predict the 5th word. So in general, I have called it as that you are given n-1 words and you want to predict the nth word. The n that I am considering here is 4, okay? Now what's going to be the training data for this? You take any corpus that you have built, anything, right? Consider all 5 word windows from there. Don't get too engrossed in the story. So there are 4, the first 4 words you can treat as x, and the 5th word would be your y, right? So you can construct many such x comma y pairs from the raw corpus that you are creating. Any 5 word window, and you can keep sliding this window, right? What I mean by that, this is your first training instance, x comma y. This could be your second training instance. So there could be these overlapping training instances. You keep sliding this window and you'll get many, many training instances, okay? You see that? So this task, the advantage is that given the size of the web and so on, at least for popular languages, the training data almost comes for free. Okay? Compare this to MNIST or any other task where you have to actually acquire these labels, that this is an apple, this is a banana and so on. Here you get the training data for free. You just need to scrape it from the web. No, so window size is something that you will set, right? Whether you want to learn 4 word windows, or what do you mean by don't know the window size? No, so this again, there is a lot of existing literature in the traditional NLP where various, a lot of work has been done to figure out what's the right N. So in most NLP tasks, right, if you want to predict the next word, a 3-word window is enough actually. If you know the last 3 words, and you can try this as a mental exercise, right? If you know 3 words, you don't really need to know the words before that. So this is the Markov assumption where there's a trigram dependency in the words, right? So this N is not really so difficult, and in the default tool that you guys would try, probably they take the value of N as 7, right? That's an overkill, but that's again, it comes from a lot of existing literature in NLP, right? This is not, this task is not deep learning brought, right? This task is a simple language modeling task which has existed for many years, right? From probably 1950s or 60s or something like that, okay? Okay, so this is all N-word windows in your corpus. As I said, training data comes for free, and for ease of illustration, we'll now focus on the case when N is equal to 2. That means I'm given 1 word and I want to predict the next word, okay? And we'll see how to model this using a neural network. So these are the 2 questions which I need to tell you: how to model this task, and what is the connection between this task and our original task of learning word representations. Okay, these are the 2 things that I'm going to answer. So we'll model this problem using a feed-forward neural network. What's the input? 1 word, okay? So say the word is sat. I'm going to represent it using a 1-hot vector, okay? And what's the output? I want to predict a distribution over all the words in the vocabulary, and I want to pick the word which has the maximum probability. That's how you did. So for example, in the case when you had this classification problem of banana, apple, orange, mango, you predicted a distribution over these 4 classes and then picked the one which had the highest probability. Exact same idea here. It's just that instead of 4 classes, now you have V classes and your V is very large, okay? But you're just trying to learn a distribution over there. And you know that in this case, or the example that you're considering, on is the actual next word. So you typed sat and the next word is on, and probably leading to sat on the chair or something like that. Right? So this is what you would want to maximize, okay? I've given you the input, I've given you the output. Give me a neural network to model this. There are a lot of hints in the diagram itself, right? You see some space between the input and the output. So what will you put in the middle layer? We'll put a middle layer there, right? Is this an okay way of modeling this task? I have an input, I want to predict an output. So I just use a regular feed-forward neural network, and let's analyze these parameters a bit more carefully, right? So I have something known as W context, I have something known as W word. I'm already using some notations from the SVD lecture. There at the end we ended with W word and W context, right? It's not clear why I'm using the same notations, but it will become clear in some time. But let's look at their dimensions, right? So we have this 1-hot vector. I have a parameter W context which I'm going to learn, right? And its size is K cross V. So what does that mean? This matrix is going to multiply by the vector and give me a K dimensional output, right? Is that clear? So I have, this is of size V. You guys always keep surprising me. I don't know why you can't do this. This is a V dimensional vector. You multiply it by a K cross V vector. So you do W into X. So you'll get a K dimensional vector. So this is K dimensional. You have a K dimensional hidden representation. Okay. And from there now, having captured this hidden representation, you're trying to predict which is the next possible class. This is the same as any other thing, right? If you had done the image classification or the MNIST digit classification, you had this 784 dimensional input vector, you pass it through a hidden layer, and then you predicted one of the 10 classes. There's nothing magic here, right? It's the same thing that you have seen before. How many of you get this? And what are the parameters? W context and W word. Okay, and we are going to focus on these parameters and understand what they actually mean. So what is the product W context into X, given that X is a 1-hot vector? So I'll tell you this. Suppose the ith entry is hot here. How many of you say it's the ith column of W context? So it is simply the ith column of W context. Why? Because you have this W context matrix. You take a 1-hot vector which has the second entry as hot. If you do this multiplication, you basically get the second column of W. Right? You can just see it. Everyone gets this now? How many of you get this now? So if you have a 1-hot vector, if its ith entry is on, you multiply it by a matrix, you will get the ith column of the matrix. Okay? So if the ith word is present in the input, then the ith element of the 1-hot vector is on, and the ith column of W context would be selected. So then what can you tell me about the ith column of W context? You see there's this one-to-one correspondence between words in your vocabulary and columns of the W context matrix. How many columns does W context have? V columns. How many words are there in your vocabulary? V. Any one word is on, only one column will get selected. And that's a unique column. It's not going to change. Right? So there is a one-to-one mapping between the columns of W context and the words in your vocabulary. That means the columns of W context are the other vector representations. Do you know these vector representations? No. These are parameters of your network. So they'll be learned. How? We'll see. Okay? So you see the intuition for W context, setting it up this way. So now I've set up the problem in a way that by parameter matrix directly gives me the word representations. Okay? But any kind of learning has to be driven by some objective. So what's that objective? It's already clear to a lot of you, but we'll just do that in a bit more detail. Okay? Fine. So this is exactly what I have just said. Now how do you obtain P on given SAT? No. So for a given training instance. So for a given training instance, you said that your corpus has been divided into those training windows, right? So it's possible that engineer, sometimes the word does not, and is not the next word. But for this training instance, what is it? And. So that's what you have to predict, right? Is that fine? And at test time, so you're saying that, what you're saying is more practical, that when I've typed SAT in the WhatsApp message, I don't want on as always the answer. So we get these 5 options, right? 3 to 5 options. So what could be that you have this probability distribution, pick the top 5 from there and show it as options. Right? So is that fine? Okay, so we are done with this. Now how do you compute P on given SAT? What's the actual operation happening there? What is the appropriate output function? This is a multi-class classification problem. Softmax, okay? This is what softmax looks like. So the probability, if suppose on is the ith word in your vocabulary, then I'm saying that the probability of on given SAT is going to be this quantity. How many of you agree with that? I mean, those who agree is fine. I'm asking why the others don't agree. What is not clear about this? I don't know how to explain this. I mean, it's just so plain obvious. What's the softmax function? Okay, first of all, you will do this aggregation. So you'll do this W word into H. That is fine, right? So you will compute this vector consisting of W word into H. Fine. What's the dimension of that? What's the dimension of that? Mod. This is k dimensional. This is V cross K or K cross V, depending on how you multiply it. So what's the output going to be? V. So you have V entries. These are dash entries. The options are normalized, unnormalized. Unnormalized. Now what does softmax do? Normalize this, and that's exactly what this formula is doing, right? You want for the ith word, you see what was the end, this product, right? This gave you a V dimensional vector. You look at the ith entry there, right? That's what you're doing here. Raise it to an exponent and divide it by the summation of all these entries. Come on, guys. This is highly disappointing. I can't teach softmax in the 10th lecture or 11th lecture of the course, right? What's wrong? How many of you get this now? You just have to ask a bit angrily, okay? Okay, so you see this, right? This is what is happening here. So you get this V dimensional vector and you're just converting it to a probability distribution using the softmax function, okay? So now this value, how did you compute this value actually? You computed this product, which is W word into H, and then you took the ith entry of that, and then this some transformation on that, the softmax transformation on that, okay? You see that? Okay. So now I can say that P on given SAT is actually proportional to the dot product between the jth column of W context and ith column of W word. Why am I saying that? So remember that this was the ith word in your vocabulary and on was the jth word in your vocabulary. So can you explain the meaning of this sentence to me? First, let's look at the first part. What is H? It's the jth column of W context. Oh, sorry. This should be I, this should be J. So this we already saw that H is the jth column of W context because I am multiplying a one-odd vector with the matrix. Okay, is that fine? And what's the ith column of W word? So what is this product actually equal to? If I say W word into H, W word into H, that's a vector, and then I'm taking the ith entry of that. So I'm saying that is the same as taking the ith column of W word and multiplying it by H. How many of you get this? This is basic linear algebra, right? There are these 4 different ways of multiplying matrices. I'm just using one of those, right? So if I multiply a matrix with a vector and then take the ith entry of that, that's the same as multiplying the ith column of the matrix with the vector, okay? Just go back and verify this, just take my word for it for now. Okay, so now what is happening is that it's proportional to the product between the jth column of W context and the ith column of W word. Is that clear now? Everyone gets this? Okay. So P word equal to I given sat thus depends on the ith column of W word. Okay. So now what can you say? So earlier we saw that the ith column of W context corresponds to a particular word. Now what can you say about the ith column of W word? It also corresponds to a particular word. So now why these two correspondences? I already had a correspondence between W context and every word in my vocabulary. Now I am saying that there is also a correspondence between W word and every word in my vocabulary. How many of you first of all are comfortable with this sentence? That every column of W word has a correspondence with some word in the vocabulary. Okay. The second sentence is every column of W context has a correspondence with some word in the vocabulary. Do you all of you agree with both these statements? Okay, that's what we have tried to prove so far. So now for every word, that means I have 2 columns waiting for it. How do I deal with this situation? Have you ever dealt with it before? The same thing happened in SVD also, right? SVD also gave you this U sigma, which was W word, and then V, which was W context. So you can always learn 2 different representations for the words. One is when the word appears as a context word, and the other is when the word appears as the target word. You get that? You see why we have 2 different representations? Okay, fine. And as I said, hope you see the analogy with SVD, right? We already saw there that there were these 2 representations. Now given all this setup, and please don't disappoint me, can you learn these parameters? With some tweaks to the code that you have written for MNIST, can you use the same code to learn these parameters? How many of you say yes? Okay, so what's the tweaks? What are the tweaks? The input changes. Instead of the image input, you have this V-dimensional input. Okay, what else changes? The output changes. Instead of a 10-dimensional output, you have a V-dimensional output. All of you are absolutely clear about this. And what's the training algorithm? Backpropagation. What's the loss function? Cross entropy. Okay, good. Fine. So for some, I'll do some more stuff on this because there's some interesting interpretations of the gradient descent update rule here. So I'll refer to the word sat by the index C and the word on by the index W. Okay, and we already saw that the appropriate loss output function is softmax. The appropriate loss function is cross entropy. Okay, so let me just look at this, right? So W was the index of the output word. So my cross entropy formula would just boil down to this. Everyone is fine with this? Okay, I'll just try to maximize the Wth entry in my Y hat. How many of you are fine with this? Okay, and that is nothing but the probability of the word given the context. Okay, now remember that H is equal to W context into XC. Okay, I'm going to call that as UC. So UC is the dash of the word sat, title of the lecture. It's a vectorial representation of the word sat. Okay, everyone is fine with that? Because that's exactly what this product is going to do. And now my Y hat W is equal to this. Because I already said it's the product of the Cth column of W context and the Wth column of W word. Okay, fine. So now I have a formula for Y hat W. What is the training algorithm that you will use? Gradient descent with backpropagation. Okay. Now let us consider one such input-output pair and see the update rule for VW. So my loss function is this. This is actually this quantity. Okay. Now I can just rewrite it as this. I have just expanded the log. So the log of A by B is log A minus log B. Okay. Now I want this quantity because this is the parameter of the network, right? VW is one of the columns of W context. or is it W word? W word. VW is one of the columns of W word, and I want to learn it. What are these column entries? So that means I'm interested in this particular gradient. Okay. So I'll start taking this. So what's it going to be? So only UC will remain here. Of all these summation terms, only one of them would remain, and you can derive the derivative, right? So this is what it is going to look like. What is this quantity? The softmax function, right? So this is what I'll get. How many of you are comfortable with this? Okay, good. So now my gradient update rule is going to look like, everyone is fine with this? I've derived this formula and I've just substituted that here, and this negative and this negative. Okay. So now let's look at this update rule. So this update rule has a very nice interpretation which allows us to understand what does the continuous bag of words model actually learn. Now suppose y hat w tends to 1. What would that mean? Your prediction is very correct, right? You're almost predicting it as probability as 1. Okay. What would happen to the update in that case? There will be no update, right? If it's 1, there will be no update. If it's close to 1, there's going to be very, very minimalistic update. That means you have already learned the VW well enough. Okay. On the other hand, if I'm very bad, if y at w is close to 0, what would happen? Just tell me the case when y hat w is actually 0. What's the update rule? Have you seen something similar ever before? Have you seen something similar before? Where? Where did you see this update rule? Perceptron. What happened when you did this? W and x came closer to each other. The angle between them actually decreased. So the same thing is happening here, right? So what you're trying to do is, you're trying to make your word representation closer to the context representation. Is that clear? How many of you get this? It straight away follows from the update rule, right? Because you're adding a fraction of your context vector to your word vector, and we know that when we add two vectors, they come close to each other. The cosine between them decreases. That is what we proved in the word to vec lecture, in the perceptron lecture, right? So you can go back and refer to this slide on lecture 2. Okay. Now, so the training objective is essentially ensuring that the cosine similarity between VW and context word is maximized. Between the word and the context word is maximized. Now, what's the result of this? Now, I want you to go back with our starting example where we said that we want to learn representations such that cat and dog are close to each other, but cat and truck are not close to each other. I want you to think, whatever you see on this slide, the conclusions that you drew from this slide, how do they help you to relate back to that initial goal? Okay, so now let me give you the intuition, right? So what happens to the representations of two words W and W prime which tend to appear in the same context C? So say dog eats, cat eats, right? So dog and cat are two words which appear with the same context, eats. So what will happen to the representation of dog? It will come close to eats. What will happen to the representation of cat? Come close to eats. Not only that, dog will also go close to pet, animal, sleeps, right? And so on. And cat will also go close to these. So transitively what will happen? Dog is going close to a certain point or certain sets of points. Cat is also coming close to the same set of points. So transitively, dog and cat will come close to each other. You get this intuition? Okay. Anyone sees a problem with this? No. So no one objected when I said that dog comes close to eats. Is that what you wanted? I mean, why should dog be close to eats? That means if I find the nearest neighbors of dog, I'll get words like eats, sleeps, barks, and so on. Is that what I wanted? So that's exactly what is happening. And based on that, I convinced you that dog and cat will come close to each other. But there's a subtle gap here. I want you to close that gap. How many matrices do we have? 2. Okay, that's enough hint. We are going to either take columns of this matrix as the representations or the columns of this matrix as the representation. Okay, not mixed. So now can you tell me? So dog here will come close to eats, sleeps, barks here. Word will come close to context word, right? Cat here will come close to eats, sleeps, and so on, right? So transitively dog and cat will come close to here, and this is the representation that you care about, not representations across these two matrices. So what I said is that the training rule ensures that the words representation comes close to the context words representation. Okay, that's what we saw with the training update rule. So that means dog will come close to any kind of context word that it appears with. So dog, I would expect it to appear with context words like eats, pet, animals, barks, drinks, and so on, right? So dog is coming closer to these words. And I expect cat also to appear with these words. And of course, I don't expect truck to appear with these words, right? So then cat will also come close to these set of words. Dog will also come close to these set of words. So transitively, dog and cat will come close to each other, right? All of them are coming close to each other, okay? Which is fine, which was my original goal. But my original goal was not that dog and eats should come close to each other. Because eats and dog are neither synonyms. I mean, they don't have any semantic, I mean, they have a semantic relation, but that's not what I wanted. I wanted similar words to come close to each other. But now I have this side effect that dog is coming close to eats. But that's bad. How can I live with that? So the key thing that you should notice is that you have one matrix of words, the other matrix is of context words. So the representation of dog in the word matrix is coming close to the representation of eats, sleeps, etc. in the context representation, on the context matrix. The representation of cat is also coming close to these words in the context representation. And transitively, because of this, dog and cat in the word matrix are coming close to each other. And this is the matrix that we care about. In this matrix, dog and eats, dog and sleeps are not close to each other, right? Is that fine? Everyone gets this now? Okay. So this is only an intuition, okay, and this becomes very tricky when I'll blow this up. What do I mean by blow this up? Right now, what am I trying to do? What is the size of n? 2, right? I'm taking one word and outputting the other word. Hence, you get all these neat interpretations that you're moving close to that vector and so on. The moment I add more words to n, these interpretations become more and more hard, right? But this, again, I mean, this is good to understand that this is what happens, at least in the best case. So this is only an intuition which is reasonable in my opinion. I haven't come across a formal proof which says that this is what actually happens. And that's one criticism for word2vec, right? It works very well, but there's no formal proof which tells you why exactly it works, right? As opposed to SVD, right? There we know there's a principle behind it. Here that is not very clear, right? But it works very well based on this intuition, okay? So everyone gets the whole setup. How we started with the classification problem of predicting the nth word given the n-1 words, which had nothing to do with word representations. That's a simple language modeling problem which has existed forever. We smartly modeled it, or someone smartly modeled it using a neural network, such that the parameters of the neural network end up giving you the word representations. And this network is end-to-end trainable using an objective function. The training data comes for free. For popular languages, you have like tons of training data, the entire Wikipedia, entire web, whatever you can scrape. That's why with more and more training data, you can learn even better and better representations. So for popular languages, the representations are really good. And then we saw an intuitive explanation for why this works, because of this movement of things closer to each other. And the key thing to note is there are two different representation matrices, one for the words, one for the context. And this is not surprising. The same thing happened for SVD also. U sigma was W word and V was W context, right? So it's all in the same spirit. Now, in practice, instead of window size of 1, it is common to use a window size of D, where D could be 4 or 7. I've even seen 11 actually, but not beyond that, okay? Now let's see what happens if you have 2. And here itself it should become clear that now those interpretations are not very neat. So what I'll use, suppose I want to take a context of 2 words, then I have he sat, and now I want to predict the next word, right? So what's my input now? He and sat, right? So I'll take the one hot representations of he and sat. I'll just concatenate them. I'll just concatenate them. Is that fine? And my input now belongs to r raised to 2v. In general, it will belong to r raised to dv, okay? And now what's the next step? Do you see something funny here? I've just created 2 copies of this, okay? I'm telling you an inefficient way of doing this. Later on, it will be a very simple thing to do a very efficient way of doing this, right? But first, just to get the math around, I'll just do an inefficient way of doing it. Why have I stacked it twice? 2 words, right? So now my H is actually going to be the sum of all the columns of W which correspond to my input words. Is that fine? I have 2. Earlier, I had just 1 word as the input. So my H was just equal to that column of W. Now my H is going to be equal to the sum of all the columns of W corresponding to the words that I have, and I'll tell you why. So I have taken W context comma W context, which is just a W context matrix stacked twice back to back. So this was my W matrix. This is my 2 hot vector because I have 2 inputs now, right? So my vocabulary size is 3. So the first 1 hot vector followed by the next 1 hot vector. And now I'm going to repeat W, W. Now what's the product of this? It's the sum of the 2 columns that you see highlighted, right? And exactly that's what I have written here. Okay, so if I do it this way, then I can just do this very expensive matrix multiplication and to do something very trivial, which is just taking the sum of 2 columns, right? But at least you get the operation, and I'll just on this next slide or something, I'll tell you an obvious simple way of doing that. So I just get the sum of the 2 columns. So that's the input to my network. If I had k words as input, if I had my window size was 4, what would it be? I would have these 4 copies of W context. I'll have these 4 1 hot vectors, and it will just give me the sum of those 4 columns. Okay, that's going to be the input. Okay, and the rest of the story remains the same, right? Once you have this H, the rest of it from there remains the same. And this is the formula for H in general. In the spatial case, it was just the ith column. In the general case, is the sum of all the columns that are there in your input. Now in practice, of course, this is a very expensive matrix multiplication. It's stupid to do it that way. What you will do is you'll just slice off those columns from W context, right, and then just add them up. So you don't really need to do that stupid matrix multiplication, because you know that the matrix multiplication is essentially just selecting these columns and adding them up. So just select those columns and add them up. So you don't do that bad matrix multiplication operation. Is that fine? Now what happens during backpropagation in this case, in the generic case? The ordering doesn't matter is what you're saying. Yes, it doesn't matter. Yeah, that's an assumption of the model. So that's why the name of bag of words. You're not relying on the sequence. So this comes from NLP, that if you rely the sequence, you call it sequence. If you're just going to take the words in the sequence, you just call it a bag of words. Because once you put them in a bag, there is no ordering there, right? So that's why the word name bag of words. So and again, P on given sat is given by this Softmax formula. Okay. Now tell me, during backpropagation, and if you give me a right answer to this, I'll really feel happy that you have understood everything right from the beginning of the course. So no pressure. So which are the parameters which are going to get updated during backpropagation? Which are the 2 large matrices? W word and W context. So obviously the answer is not W word and W context, otherwise I wouldn't have asked you. The answer is some dash of these 2, some subset of these 2. Okay, which subset? Let's start with W context, which is the input. Are we going to update the entire W context? Did it participate, the entire W context participate in the computation? Only those columns corresponding to the words. So only those parameters will get updated, right? So how many columns will get updated? D columns, right? W word, will all the columns of W word participate in the computation? How many of you say yes? Okay. How many of you say no? The others don't care. Can you just focus on this circle? Did all the columns of W word participate in the computation? You see the summation at the bottom? It's over all the columns of W word. All of them participated. So the parameters which will get updated are W word and all the columns of the input words. Okay. And same backpropagation will work again. Is that fine? Okay. So remember that, and this is, I cannot emphasize it enough. Whatever I have explained is only for an intuitive explanation. You will never ever do this matrix multiplication, right? And that's why what you're going to do is you're just going to select those columns, add them up and feed them. And the network will take care, or rather you will take care that you update those parameters only, and you don't update the entire W context matrix. Because anyways, there's no gradients flowing to the other components. So remember that in the practical implementation of W of word to vec, don't search for this matrix multiplication at the input. Or if you're writing the code on your own, which is highly unlikely, don't do it that way, right? So if you, whatever code that you look at, they'll not have this complex matrix multiplication at the beginning. They'll just pick up the columns and add them and feed them, right? And I think the TensorFlow way of doing is, you have this word embeddings matrix and you can slice columns from there and so on, okay? This is fine. So everyone understands this so far. Now, what are the problems with this? Why is this not as simple in some sense as the MNIST dataset? Again, focus on the circle. This softmax computation is a very expensive operation, right? You have a V cross K sized matrix somewhere there, and unlike at the input, here you will have to do this matrix multiplication, right? So you have a V cross K matrix multiplied by a K cross 1 vector, and there's no simplification of this. You have to do this multiplication. What are the sizes of V that we saw in practice? 50K, 100K, and if you're Google, 13 million or something like that. So this is not feasible. We cannot do this expensive matrix multiplication, right? So although all of this works very fine, we need to think of ways to simplify this softmax computation, where the denominator requires a summation over all the words in the vocabulary. So you have to do that many matrix multiplications, okay?